Today I will be talking about quantum tunneling. Tunneling is a phenomenon where subatomic particles, mainly electrons and protons, pass through a potential energy barrier despite the particles seemingly having insufficient energy to do so, which violates the principles of classical mechanics. Friedrich Hund was the first person to analyze this in 1927, shortly after Erwin Schrödinger published his equation, and a year later, George Gamow used tunneling to explain the radioactive alpha decay of atomic nuclei. For an analogy, imagine a ball rolling with a kinetic energy of 100 joules. The ball encounters a hill where the potential energy is 10 joules. The probability the ball passed over the hill is 1. The ball passed over every time. But if the height of the hill is increased so that the potential energy is 200 joules, the probability will be 0. It never makes it over the hill. The existence of the ball beyond the hill is energetically forbidden. However, according to quantum mechanics, the ball, along with all matter, has a wave function which is defined over all space. The wave function may be highly localized, but there's always a chance the ball reaches the hill and will suddenly be found beyond it. In reality, this will never happen as the ball follows the rules of classical mechanics. Tunneling occurs because of the wave nature of matter. The quantum wave function describes the state of a particle, and the wave equation, such as the Schrödinger equation, describes their behavior. The probability of transmission of a wave packet through a barrier decreases exponentially with a higher barrier height, width, and the particle's mass. So tunneling is seen mainly in low mass particles such as electrons and protons. The Heisenberg uncertainty principle states that if we know a particle's energy or momentum, then we cannot be certain about the position of the particle. Probability must be used to determine where the particle is most likely to appear. This only applies to small particles, as large objects' momentum will be much bigger than Planck's constant divided by 4 pi. There's always an extremely small chance the particle can be found beyond the barrier. A finite height square potential energy barrier is defined by the following potential energy function. There are three different regions. In region 1, an instant wave packet moves in a potential free zone and coexists with a reflected packet. In region 2, a part of the instant wave packet not reflected moves as a transmitted wave packet in a constant potential and tunnels through to region 3, where the wave packet that has tunneled through the potential barrier moves as a free particle again. If the height of the barrier is infinite, the wave packet cannot penetrate it and bounces back like a classical particle. When the height and width are finite, a part of the quantum wave packet instant can penetrate the barrier boundary and continuous motion inside the barrier where it is gradually attenuated on its way to the other side. By solving the boundary value problem for the time-independent Schrödinger equation, a smooth continuous function and the general solution for each region can be found. Assume the height of the barrier is greater than the energy of the particle, as this would be the case where quantum tunneling occurs. In region 1, the potential energy part of the equation is equal to 0, so it simplifies to what is shown above. The equation can be rearranged to get in this form. The general solution is an exponential form with complex exponents rather than trigonometric form because it's a traveling wave taking the instant wave and reflected wave into account, with the A part being the instant wave and the B part being the reflected wave. The trigonometric function will be used in a potential well. The continuity conditions at region boundaries require that wave function 1 is equal to wave function 2 at x equals 0, and the derivative of wave function 1 is equal to the derivative of wave function 2 at x equals 0. In region 2, the equation is rearranged to this, which is similar to region 1 but slightly different. Beta squared is positive because the height of the barrier is more than the energy of the particle, and beta is a real number. The general solution is not oscillatory and is in the form of exponentials that decrease, that describes a gradual attenuation of wave function 2. The continuity condition at region boundaries are similar to region 1, but with L and x equals L instead of x equals 0. In region 3, it's like region 1, where it's in exponential form with complex exponents. Since there is only one wave, the transmitted wave, the constant g must equal 0. The two types of solutions in the three regions with oscillatory behavior in region 1 and 3, where the particle moves freely, and exponential decay behavior in region 2 is shown in the visual reference above. The transmission or tunneling probability is the ratio of the transmitted intensity to the instant intensity. Further boundary condition calculations can be done to find equations for the constants A and F. Quantum tunneling can come across as an obscure or even unimportant phenomenon, but it has a wide range of applications, and without it, none of us would be here. Quantum tunneling is the reason the sun shines. Nuclear fusion happens in the core of the sun, where hydrogen atoms are turned into helium atoms when they fuse together, and it releases light. as energy. Two protons must come close enough together to form a nuclear bond, but they repel each other since they are both positively charged. Quantum tunneling allows this to be overcome and for the strong nuclear force to take over, creating the nuclear bond. The scanning tunneling microscope can be used to see individual atoms. It applies a voltage to the scanner and the sample it's examining and passes the metal tip of the scanner very close to the sample. Some electrons pass through the gap due to tunneling, completing the circuit. Tiny bumps on the surface increase and decrease the level of current, so the microscope can record the shape of the surface. This can be used to map DNA strands or build new materials atom by atom. And most scientists believe that quantum tunneling could hold the key to the secrets of our universe.